Now let's consider a more concrete problem with the real numbers. So we are considering like a similar geometry, but here we have specific numbers. For W1 we have 30 millimeter, H1 we have 40 millimeter, W2 we have 90 millimeter, H2 we have 20 millimeter, and the elastic modulus, the Young's modulus, is given as 165 gigapascal. Then applied moment under pure bending is given as minus 3 kilonewton meter. Okay, which means that it's negative sign convention, and you can imagine the bending of the beam in this kind of way. So this problem asks us to obtain the maximum compressive and tensile stress, and to obtain the bending radius of curvature. To obtain the stress distribution, we have to use the flexure formula, which is minus y over I multiplied by applied moment m. However, given this geometry, we don't know how to get I, and we don't know where is the origin, which is the centroid position. So what you have to do first is we have to first figure out the location of centroid. Then we move on to performing the calculation for area moment of inertia. Having obtained y equals 0 position and I, then we can apply flexure formula, and we can also obtain the bending radius of curvature. So when you look at this, it looks quite similar to our previous example. So you can imagine our blue rectangle with width 30 millimeter, height 40 millimeter, and the upper part, let's call this as our red rectangle. Okay, then if we divide the problem into two parts, blue part and red part, and it's really easy to obtain the centroid for blue part. The centroid for blue part, let's use blue color. It's 20 millimeter. Centroid of red part, this distance, 40 plus 10, it's 50 millimeter. Okay, it must be halfway through of the each rectangles. Then after identifying this, we obtain the area for blue one, and the height divided by 2 for blue one, which is 20 millimeter, and we obtain the area for red one, and obtain the height, which is 50 millimeter. And obtaining W1 and H1 and W2 H2 is really easy. It's like 1200. Regarding the red one, it's like 1800. Okay, so after plugging all those numbers, what you're gonna get is y prime bar is 38 millimeter. Okay, so you can identify that this is centroid of entire cross section. Okay, and this distance turns out to be 38 millimeters. Okay, so having obtained that this is 38 millimeter, it's quite easy to obtain D1 and D2. So you can see that the D1 is 18 millimeter. This is D1. You can obtain D2, the distance from centroid to the centroid of red one. D2 is 12 millimeter. This is D2. Okay, after identifying D1 value and D2 value, then you can apply our previous knowledge. So when we obtain y squared dA integral when y equals 0 is here, then you apply the parallel axis theorem. This is the area of moment inertia for blue block with respect to its own centroid. This is area of moment of inertia for red block with respect to its own centroid point, and this is area multiplied by D1 square. This is area of second part, which is red block, multiplied by D2 square, which is 12 and 18 respectively. After plugging in all those numbers, you're gonna end up having 868,000 millimeter force power. Okay, so this is the value for I. Having obtained the value for I, and having obtained the location of the centroid point, then we can apply the flexure formula. So let's try to get the answer for first problem. So as I told you, we have negative sign moment m minus 3 kilonewton meter, which is crying phase, and you can expect that there's gonna be tension and there's gonna be compression under the pure bending. Then we can obtain the maximum distance from the centroid in upper part. We call that as a CU, which U refers to upper part, and the distance from the y equals 0 in down part, we're gonna call that as minus CD. Okay, and we're gonna apply this to flexure formula. So we're gonna expect maximum tension at the top surface, and at top surface CY is 22 millimeter. It's gonna be 22 millimeter. And about the bottom part, distance to this bottom, it's minus 38 millimeter. Then we simply apply and plug this into the flexure formula. 22 here, minus 38 to here in the place of y. Okay, and we plug in the value of I, and then we also plug in the value of applied moment m, which is minus 3 kilonewton meter. After plugging numbers, we're gonna get maximum tension with 76 megapascal, maximum compression with 131 megapascal. And having obtained these values, we can answer the first question. And regarding the second question, obtaining the bending radius of curvature, we simply apply this equation: 1 over rho equals to b, apply the moment, absolute value divided by EI. Then you simply plug in numbers that we obtained in previous page, and we end up getting this value as 1 over rho. Okay, and if you obtain the inverse value of this 1 over rho, you obtain rho equals to be 47.7 meter. Okay, so you can see that bending radius curvature is quite small for this material property, 165 gigapascal with applied moment of 3 kilonewton. Okay, so with that, we were able to answer 2 questions in the question 3. And this somehow demonstrates how to apply flexure formula for complex cross-sectional shape. Okay, to apply flexure formula, you have to know the origin of the flexure formula, which is the centroid, and you have to also obtain the value for I. And when obtaining I, you have to do this integral, and to do that integral you also need the position of centroid. And if you have the intuition from general physics, you can apply the parallel axis theorem. Then after that, we obtain both centroid position and value of I. We can simply plug the numbers into flexure formula to answer various pure bending problems. Okay, so this is the logical flow of approaching pure bending problem.